complex analysis out of the Complex Variables and Applications textbook by James Ward Brown and Ruel V. Churchill. It is the 7th edition of the textbook. I have requested from my professor the exercises that we will be doing for sections 14 through 17, which all share the same exercise section on page 53, and I've received the questions from him. That means we can work on any question that is not on that list without violating any academic dishonesty rules. So let's work on number 2. Let me write these down. So we can work on number 2, 4, 6, 8, 9, and 12. So that's a good 6 problems. I think that is great amount of practice right there. 6 problems sounds like a great amount of practice. So we're going to start on number 2. So number 2. Let A, B, and C denote complex constants. Then use definition 2, section 14 of limits to show that the following are true. The limit as z approaches z naught of az plus b equals a z naught plus b. B, the limit of z squared plus c equals z naught squared plus c. And I'm going to add the naughts in after. And then part C, we have limit as z approaches 1 minus I of the following expression, x plus I 2x plus y equals 1 plus I or z equals x plus iy. And we will write the constants down now. And we can go z approaches z naught here. Z approaches z naught here. And finally, we have z approaches 1 minus I here. So we have a statement we need to recall, which is the definition of limits from section 14. So I shall put that up on the screen. We shall recall definition 2 of section 14. The limit as z approaches z naught of f of z equals w naught and then we're going to have the font size 10 naught here. Means for each positive epsilon, there is a positive delta such that the distance between f of z and w naught is less than epsilon whenever the distance between z and z naught is less than delta. So what does this mean in the context of our problem? Well, for part A, thus part A of the problem means for each positive epsilon, there is a positive delta such that the distance between f of az plus b minus az naught plus b is less than epsilon whenever 0 is less than z minus z naught is less than p, or delta. And then we have our little naught symbol here. And we have our little naught symbol here. And we just want to double check that this is exactly what our problem means. So we substitute in f of z. And f of z with an input. Let me double check I wrote the problem down correctly. the limit of az plus b that should be a complex number, right? Or should it just be that? Because the function should be az plus b. And then when we put z through there, then we should get that. And then we get the limit whenever z is less than z naught. All right. Well, this implies let's be careful here because I think there should be parentheses right here. I think that's correct. No. So this implies that the distance between AZ and AZ naught is less than E whenever epsilon, whenever 0 is less than Z minus Z naught is less than P. But this also implies that Z minus Z naught is less than epsilon divided by A whenever 0 is less than Z minus Z naught is less than P. Well, let P equal E over A. And we are done. What does this mean for part B? So thus for part B, let's make that smaller, make this longer. Draw a line right here. And draw a line right here. Now we're all organized. Let me just move the computer into my lap. But now, this means for each positive epsilon, there is a positive phi such that the distance between z squared plus c and the distance between z naught squared plus c is less than epsilon whenever the distance between z and z naught is less than p. But this implies the distance between z squared and z naught squared is less than e whenever 0 is less than z minus z naught is less than p. Okay. So this should be z plus z naught times z minus z naught. I have no idea if this is the right direction to go in, but I will go in this direction nonetheless. Whenever 0 is less than z minus z naught is less than v. This doesn't seem right to me. And the reason why is because the distance z minus z naught can stay constant, while the modulus of z plus z naught can increase to any degree we like. So I don't feel comfortable with this. Did I read the problem wrong? No, I did not. Well, if the distance between z and z naught is less than p, then that means z plus z naught is being scaled by p. Hmm. All right. Let's z plus z naught I don't feel like I can do this. I don't feel like I can let it be equal to something. If I let it equal epsilon and let p less than 1, then it should work. I want to double check this with the professor. But for now, we can move on to part C. So this means for each positive epsilon, there is a positive delta such that x plus I times 2x plus y minus 1 plus I is less than epsilon whenever z minus 1 minus I is less than phi. Wait a minute, this was supposed to be a plus right here. I goofed. So this is supposed to be a plus. Alright, why is this true? Or what does this imply? So this implies that z minus 1 plus I times 2x plus y minus 1 is less than epsilon whenever z minus 1 plus I is less than phi. So these are almost the same thing, except they have different complex parts. So I'm not really sure where to go from here. So revisit this. So revisit part C. So we're going to call this section 17, problem 1, no, problem 2, JPEG. And we're going to copy this, new file, paste that here, and we're going to go on to number 4. So number 4, use mathematical induction and property 9 from section 15 of limits to show that the limit as z approaches z naught of z to the n which I will finish that in a minute, equals z naught n z n, the limit as z approaches z naught. And then we zoom in a little further, drag this up here, drag this up here, I think the first step of this is to recall property 9 of section 15. So recall property 9 of section 15. All right. The limit as z approaches z naught of f of z, capital F of z, equals w naught, capital W naught, as z approaches z naught. We're going to have suppose that the following are true. And that implies those are going to imply this. Suppose that the limit of f of z equals w naught All right, so we're gonna just make this a little larger. We're gonna drag this a little bit down. So first, I think it's appropriate that we write proof. And we're going to choose a value for of n to prove the theorem for. No, actually, induction is base case and then induction step. So suppose we will show observe by property 9. Actually, suppose this bit right here. Then, by property 9 of section 15, we have the limit of f of z squared equals w naught squared. Now, we're going to suppose the limit of f of z to the n minus 1 equals W naught to the n minus 1. As z approaches z naught. Then we have, by property 9 of section 15, this thing but this implies what we were trying to prove. And thus our proof is complete. Fantastic. So we're going to save this file as section 17 problem 4, section 17 problem 4, and we're going to save this as a JPEG. And we're going to start a new page, and we're going to start on number 6. So prove, so number 6, prove statement 8 in section 15 and properties of real valued functions of two real variables. Using, and we have to use for part A, theorem 1 in section 15 and properties of limits of real valued functions of two real variables. And then for part B, we have to use definition of 2 of section 14. Well, first, we need to recall statement 8 of section 15, which I shall look up in the textbook. All right. The sum of the limits equals the limit of the sum. So we've got some knots to type. And we've got some hypotheses to suppose. Suppose the limit of f of z equals w naught. And we're going to go capital F of z equals capital W naught. Then all right. So we're going to write in green, prove the sum of the limits equals the limit of the sums. And this is as plain English as I can write it. I do not know how to write it in any more plain English. All right. So we need to use theorem 1. So for part A, recall theorem 1 of section 15. Suppose f of z equals u of xy plus iv of xy z naught equals x naught plus iy naught, and w naught equals u naught plus iv naught. Let's put in the naughts. So then we can deduce by this the limit of f of z equals w naught as z approaches z naught. All right. Well, I think the proof is going to be fairly straightforward. So we're going to write a proof. And the reason why I'm saying this is straightforward is we have the sum of the limits equals the limit of the sums. And we have the limits, so we can just take the sum of the limits, and then we should get that is equal to the limit of the sums. So we're going to suppose this. And we're also going to further suppose f of z equals capital U of xy plus I capital V of xy and capital Z naught equals capital X plus I capital Y, and capital W equals capital U plus I capital V naught. And we can insert the knots now. Well, then we have this equation plus this equation. So we're going to put a little plus sign right here. And we're going to put a little plus sign right here. And we're going to drag these together. We're going to drag these together. And we're going to drag these together. Um, but we're going to have a limit here. And we are also going to have a limit here. So we're going to color with green and purple to show what I am corresponding these to. So we have green, and we have green, and we have purple, and we have purple. Actually, I don't think this is right. I don't think that is right. Okay. I've been working at this for almost an hour. So I think what I'm going to do is I am going to save my work. And then this is going to be section 15, problem 6, and this is going to be a JPEG. And then I'm going to end the stream here, and I can resume next time.